Okay. Hello everyone. I'm Chungkuk, a PhD student in KAIST. Today we present SymmetriSense, a novel mobile platform to enable near surface interactivity above glossy surfaces of everyday flat objects. The beauty of SymmetriSense is that it requires only a single commodity smartphone. This work was done when I was an intern at IBM Research Austin with Inseok Hwang, Eric Rozner, Yu, and Robert Dickerson. Imagine that you can interact with large glossy surfaces of everyday flat objects. For this, the only requirement is a single commodity smartphone you already have. You can define your own interface above a raster mirror so that you can instantly make the 3D interactive mirror with your smartphone. Also, you can enjoy a game on a normal TV screen which doesn't have a touch feature. If this kind of interactivity would be realized above your everyday object, then the everyday object would be much smarter and tons of interactive applications could be served on them. It will be a new opportunity to provide new user experience. To this end, we propose SymmetriSense. It is a mobile platform to enable interactivity above a glossy surface of everyday flat objects. Our SymmetriSense runs on a single commodity smartphone and localizes the fingertip 3D position above a surface in real time. This video shows demonstration of the SymmetriSense on a TV screen, but not limited to this setting. The platform can be adopted to any glossy surface of everyday flat objects. I guess many of you may be curious about what is new in the surface interaction. Yes, many researchers have proposed finger tracking techniques for surface interaction. This video shows existing works for finger tracking on a surface. The fingertip location above a surface can be represented by the x and xyz coordinates. To calculate the coordinates, we need the information of the distance between the reference point and the fingertip. To get the distance, existing techniques use infrared LED, infrared camera, depth camera, or a pair of stereoscopic camera. We say that such specialized hardware is the problem making general penetration very difficult. Normal users don't have such specialized hardware now. That's the reason why the surface interaction technique still does not come into our everyday life. Our research started at the question, how can we enable the surface interaction using a commodity device, such as smartphone? Everyone always carries a smartphone embedding a camera and a computing unit. If possible, you can instantaneously make non-interactive surfaces interactive in your everyday life. However, it is not simple to localize the fingertip position using a single commodity camera. The two pictures show two different fingertip locations on the surfaces. The smartphone's camera looks downwards to capture the fingertips location. Let's see the fingertips from the camera's field of view. Using only these two pictures, can we pinpoint the fingertips location in the 3D space? No, we can't. If the two fingertips are located on the same line of the site, the fingertips image in the camera's field of view appear at the same position as shown in the right two pictures. Because of the ambiguity in the fingertips location, existing works requires specialized hardware to pinpoint the fingertips location. But we found that the reflection of the fingertip on the surface can be used to localize the fingertips position. As shown in the right two pictures, the rear image of the two fingertips still remain at the same position in the camera's field of view. However, the reflection of the two fingertips appear at different positions in the camera's field of view. We focus the reflection phenomenon to localize the fingertip 3D position above a glossy surfaces. Only requirement of the SymmetriSense is that it runs on a glossy surface. In our everyday life, we frequently meet glossy surfaces such as restroom mirror, office windows, grainy kitchen countertop, whiteboard, and so on. You may want to know how to calculate the fingertips location with the reflection. We will explain how to calculate the y distance. With the y distance, we can easily compute the x and z coordinates. Please refer to our paper for how to compute the x and z coordinates. This is the basic setting of SymmetriSense with a glossy surface and a commodity smartphone. The right cross-section diagram simply shows the situation of the left picture. We already know the length of the line segment CH and the camera's mounting angle theta m by actual measurement. When the fingertip is located above the surface, the reflection of the fingertip also appears. We want to know the y distance to localize the fingertip 3D position. By vision sensing from the camera's field of view, we also can calculate the angles, the angle theta r between the center of the camera's field of view and the reflected fingertip, the angle theta o between the reflected fingertip and the real fingertip, the angle theta c, the complementary angle. Then how can we compute the y distance with the known variables? From the cross-section diagram, we have the two geometric identical equations. As shown in the diagram, the length of the line segment OR is the same as the length difference between the line segment RY' and OY'. Also, the length of the line segment RY is the same as the length difference between the line segment RY' and YY'. Then, we can represent the two line segments OR and RY with respect to the y distance. At this point, by the principle of reflection symmetry, we can equate the two expressions. Then, the y distance is given by the known variables. Please refer to our paper for more details about the geometric calculations. Then your next question may be how to extract the fingertip and its reflection in the camera's field of view. Our intuition was that in the camera's field of view, the moving part would be the fingertip and its reflection. Here are two subsequent frames from the camera's field of view. By interframe differentials, we can extract the areas of moving finger and its reflection part. After computing convex Hall, including the areas, we can get the position of the fingertip and its reflection from the camera's field of view. Note that this fingertip extraction is not our contribution. To run SymmetriSense in real time, we adopted the well-known lightweight vision technique to fingertip extraction. We believe that an advanced vision technique for fingertip extraction would be helpful to improve the accuracy of SymmetriSense. We implemented SymmetriSense on a commodity smartphone, Galaxy S5, but our SymmetriSense can run on any off-the-shelf mobile platform which has a camera and a computing unit. Considering the limited computing resource of the smartphone, we used the low vision resolution for the fingertip extraction. SymmetriSense run in real time as taking 25% of the CPU utilization on the smartphone. The image processing for the fingertip extraction takes 8.7 milliseconds per frame. Our test at 640 by 480 vision resolution took 50 milliseconds per frame, which cannot run in real time. To smooth localization error from the low vision resolution, we used 10-frame moving average. we evaluated the accuracy of SymmetriSense above the 60-inch TV screen. For the experiment, we recruited 18 participants who consisted of mixed ethnic group, age, left and right-handed people. Each participant pinpoints the center of the target circle, which size was 50 millimeters on the TV screen. We measured the arrow distance in the XY plane between the center of the target circle and the XY coordinates from SymmetriSense. The average error was about 10 millimeters. According to a survey, the average width of the index finger is 16 to 20 millimeters for most adults. So, we believe that the arrow distance of 10 millimeters would fit with a finger interaction above a surface. We have a plan to study about design guidelines of an interface provided by SymmetriSense, such as what is the good object size for pinpointing, what is good distance between objects with the arrow distance. This figure shows the raw result of pinpointing task for the experiment. We observed the tendency to increase the distance error along the y-axis. As you can see, the arrow distance is small at the close area to the camera, but at the far area from the camera, the arrow distribution is large. This cross-section diagram simply shows the reason. When the fingertip is closely located to the camera, the vision sensing error might not much affect the y-distance error. However, if the fingertip is far from the camera, the y-distance error would be increased even for the same vision sensing error. This inherent vision sensing error is bounded by the angular distance of a single pixel in the camera's field of view. As decreasing the vision sensing resolution, the angular distance of a single pixel increases. So, in case of the low vision sensing resolution, a single pixel error makes big distance error, such as 25 millimeters, under 320 by 240 vision resolution. To reduce such a big error, we used 10-frame moving average to smooth the distance error. As we mentioned, we used the low vision resolution because of the limited computing resource of the smartphone. Accelerating image processing by using mobile GPU or computational approach to a cloud would be helpful to improve the computing power, thereby adopting higher vision resolution. Then SymmetriSense could achieve higher localization accuracy with the higher vision resolution. We also measure the localization error in terms of Z height, perpendicular distance between the fingertip and a surface. We tested the Z height error at 10, 30, 50 millimeters above the surface. The arrow distance of Z height was less than 2 millimeters on average. We also tested robustness of SymmetriSense in terms of ambient brightness condition, surface background color, and display brightness. The results say that there is no statistical difference in the accuracy except the complete darkness case. SymmetriSense doesn't work in the complete darkness case because a commodity camera of a smartphone cannot capture anything in the complete darkness case. Note that we performed the robustness experiment on the 5-inch smartphone screen because the small screen is easily movable to various places for the experiment under various ambient brightness conditions. So, the fingertip is closely located to the camera rather than that of the TV screen case. As we mentioned about the error tendency, The small screen case shows the smaller error distance, such as 2 millimeters, while the error is 10 millimeters in the large TV screen case. To recap, we presented SymmetriSense, a novel mobile platform to enable near-surface interactivity. It runs on a single commodity smartphone and any glossy surface of everyday flat object. SymmetriSense achieves the fair accuracy for finger interaction. Please refer to our paper for more details. Thanks for your listening.
Thank you. Questions right here.
It's really short. Hi. Daniel Ashbrook, Rochester Institute of Technology. I'm curious if there is a difference in performance with the reflectivity of the surface.
Oh, that's the good question. Actually, we verified the performance of SymmetriSense on the various surfaces like office window, granite kitchen countertop, whiteboard. But the rigorous measurement is our future work on the various reflectivity. Yes.
Okay. And one more question. So you gave very briefly the Z accuracy. How well can you actually detect touching?
Yes, actually, we left the robust touch feature is to our future work. Actually, we were very cautious in the detecting a touch. We observed the SymmetriSense often doesn't clearly distinguish the fingertip contacting the surface because of some because low visual resolution. So we will, if we can define the touch loosely, accepting the very tiny gap to the surface, then we believe that we can say touch support.
You could also try using the phone's accelerometer.
Yes.
So I was wondering, after the in the study results that you showed and the 10 millimeters that you reported, is that after the moving average or before?
Yeah, after the moving average.
Because it would have been really interesting to get the sort of a raw sense on the accuracy of the method, because I noticed that in the videos you were really deliberate, right, in moving the finger around. And sort of this leads me to my second question. Did you ever play around with the update rate of the camera? Because I mean, some of the commodity phone cameras you can set in a high-speed mode.
Yeah.
You sacrifice resolution, and that doesn't seem to be a problem in your case.
Yeah, but the smartphone Galaxy S5 support the 30 frames per 30 frames per second, so we use that frame rate.
Did you ever play around with high frame rates?
Not yet.
So my second question is, I noticed that when you displayed the error in Z at the very end, it seemed almost systematic. As you approached, the Y went down and went up again as you withdrew. Can you not factor in the Z into the Y prediction?
Yes, actually, as we mentioned about the error tendency along Y-axis, but this kind of error tendency also appear along the Z and X-axis. So, yes.
Great. All right, let's thank the speaker again.